First, we're going to talk about current. And current flows differently across resistors when they're in series versus when they're in parallel. And what we want to look at is how much current flows across resistors whenever they're in series versus when they're in parallel. So first, we'll just think about resistors in series. So say we have two resistors, Rg, which is R greater, and Rl, which is R lesser. So greater resistor means that it has more resistance, and then conversely, lesser is it has smaller resistance, has less resistance. And we're going to model these with two different straws. For a resistor that has greater resistance, we're going to have a smaller straw, because a smaller straw is more restrictive and therefore more resistive. And then on the other end, for RL, our lesser, if it has less resistance, we're going to use the bigger straw, because if it's bigger, it's less restrictive and therefore less resistive. So whenever they are in series, whenever they're end to end, we're going to have current, represented by cola, that's going to flow through both of these equally. The total current that goes in is going to come out the other end, and it's going to flow evenly through the two. So the current across Rg and the current across Rl is equal to each other and equal to the total current. Now, this is going to change whenever we have our resistors in parallel, because what's going to happen is the current's going to come in and then it's going to hit this node that branches off two ways. One way goes to Rg and one goes to Rl. And so what we want to know is how much current flows across Rg and how much flows across Rl. And if we think about it as two different straws, we would think that whenever it splits, if we have a bigger straw, which is RL, then we're going to have more current flowing through there because it's less restricted. So a greater fraction of the total current is going to flow through Rg compared to RL. But it's going to be a fraction of the total current because the current that's going into one node at one end of these two resistors is going to have to come out at the other end. This relationship between the current across each of the resistors whenever they're connected in parallel is explained by the current divider. And it can be shown with these formulas. So if we're looking at the current across the lesser resistor, the resistor with the least resistance, we would say that that is the total current times the fraction of the greater resistor. And conversely, if we're looking at the current across the greater resistor, we would say that is the total current multiplied by the fraction of the lesser resistor. And these formulas logically make sense, because if we have the smaller straw, the one that was more resistive, it makes sense that less current is going to want to flow through it because it's harder to flow through. And that's why whenever we have the current through the greater resistor, the one that was smaller and more resistive, it's proportional to the value of the smaller amount of resistance, and therefore the amount of current that's flowing through the greater resistor is smaller. Now we'll talk about voltage and how it behaves across resistors in parallel and in series. To demonstrate voltage, we'll use V8 as our voltage, or our potential difference, and we'll use sponges as our resistors. So the larger sponge we'll call Rg for greater resistance, meaning it's more resistive, and the smaller sponge we'll call Rl for lesser resistance, meaning it's less resistive. The voltage drop across resistors in parallel is the same regardless of the value of the resistor, because at the top node you have one value for voltage, and at the bottom node, where the two branches come back together, you have another voltage, and in this case we'll say it's ground, so the voltage is 0. And this means that regardless of which pathway you take, the voltage has to decrease by the same amount so that it can get down to 0 volts at the bottom. And if we think about this in the case of sponges as resistors, we can think that the sponge, or the resistor, has to soak up the same amount of voltage regardless of how big the sponge is. Now we're interested in determining the voltage drop across resistors in series. And we know that when we have resistors in series, together they account for the total drop in voltage across the entire circuit. However, the voltage drop across each resistor is not the same. It's proportional to the size of the resistor. If the resistor is greater, it accounts for a greater fraction of the voltage drop. And if it's smaller, a smaller fraction. And this is demonstrated with our V8 and our sponges. Remember, our V8 is our voltage, and our sponges represent the resistors. So when we have a voltage on one end of the circuit, like the V8 entering the bath of the sponges, we have a certain amount of voltage that has to be diminished by the time it reaches the other end of the circuit. Essentially, all of the V8 or the voltage needs to be soaked up by the sponges or the resistors. And, like you would guess, a larger sponge is able to soak up more of the V8, more of the voltage. Therefore, whenever we have resistors in series, the larger resistor accounts for a greater voltage drop, and the smaller resistor accounts for a smaller portion of the total drop in voltage. The relationship for the voltage drop across resistors in series can be shown with the voltage divider equation, which essentially shows how voltage is divided across each of the resistors. The voltage divider equation shows the proportional relationship between a resistor and the voltage drop across it. To determine the voltage drop across the lesser resistor, the smaller sponge, we say that the total voltage multiplied by the fraction of the smaller resistor is equal to the voltage drop across the smaller resistor. And by the same token, the voltage drop across the larger resistor, Vg, is equal to the total voltage multiplied by the fraction of the greater resistor, of the fraction of the larger resistor. Therefore, resistors with a larger resistance value have a greater voltage drop, and this is seen with the sponges, which act as resistors. The larger sponge was able to soak up more of the V8, more of the voltage, and therefore there was a greater voltage drop across the larger resistor.